There are 5 double angle identities that we want to be very familiar with. There are 3 identities for cosine and 1 for sine. And we call these our double angle identities because in the input for both sine and for cosine, the input is a double angle. So it's some angle A and it's twice that angle. Sometimes we don't want to work with twice an angle on the input of our function, but we would prefer to write it as just an angle, so an angle A, a much simpler input. We're going to verify all 5 of them. We're going to show where they come from, and the nice thing is that they all follow very easily from the sum and difference identities. So if you have the sum and difference identities memorized, you can always generate the double angle identities using those sum and difference identities. So let's look at the first double angle identity. Let's look at the one for cosine. So cosine of 2a is equal to cosine squared a minus sine squared a. So we want to verify that this is actually an identity, that this is true for all angles A, for any angle A rather. So let's start with cosine 2a, and we're going to rewrite this. And all of these we're going to make note of the fact that when we are talking about cosine of 2a or any trig function, if 2a is the input, this is the same thing as cosine of a plus a. So without changing what's on the inside, we can actually rewrite it as an angle plus itself, which is the same thing. If I add those two together, it's the same thing as 2a. So we are going to rewrite this as cosine of a plus a. And we're going to use the sum identity to rewrite this as cosine a times cosine a minus sine a times sine a. So we're just using the sum identity for cosine, cosine of the first angle times cosine of the second angle. Now the angles happen to be exactly the same, they're both a. Minus, so if we're adding on the inside, we are subtracting. We use opposite sign in between for cosine, and then sine of the first angle times sine of the second angle. Since the angles are the same, cosine a times itself, we can write that as cosine squared a minus sine squared a. So we have just verified and shown that we can start with cosine of a double angle and show that it is always equal to cosine squared a minus sine squared a. So that angle, we have met our goal, and that identity has been verified. We're going to use this result as we go to show the next 2 double angle identities. So for the next identity, we want to show or verify that cosine 2a is equal to 1 minus 2 times sine squared a. So we're going to use the previous result. We have already shown that cosine of 2a is equal to cosine squared a minus sine squared a. So we want to show that we can achieve the right-hand side. So we're going to do a replacement. Let's use our Pythagorean identity. Cosine squared a plus sine squared a. We know that this is equal to 1. This is our Pythagorean identity. And we notice that our goal is written only in terms of sine. There is no cosine on the right-hand side of this identity. So let's get rid of cosine squared a. Let's replace that with an equivalent expression using our Pythagorean identity. So we're going to come over here and we're going to rewrite the identity in terms of cosine squared a by itself on one side. So I'm going to subtract sine squared a from both sides, and we see that cosine squared a is equivalent to 1 minus sine squared a. So everywhere I have a cosine squared a, I can replace that with the equivalent expression 1 minus sine squared a. So we're going to replace cosine squared A with 1 minus sine squared A. Now we're going to bring down sine squared A. And we have 1 minus sine squared A minus sine squared A. This is the same thing as 1 minus 2 times sine squared A. And that was our goal. So using the previous result for cosine 2A, that double angle identity, we can do a Pythagorean replacement, and we can show that cosine of 2A is also equal to 1 minus 2 times sine squared A. So this is another identity that we want to be able to either derive or have memorized for that double angle identity for cosine. And our last identity, double angle identity for cosine, we're going to do very similar things. We're going to take the left-hand side and we're going to show that we can write it as 2 times cosine squared A minus 1. We're going to use that first result. We're going to use that first double angle identity. Cosine 2A is equivalent to cosine squared A minus sine squared A. And we want to show or prove that we can achieve the right-hand side. We're going to use one of our Pythagorean identities again. So we're going to go back to cosine squared A plus sine squared A. We know that's equivalent to 1. And we notice that the right-hand side, our identity, is only in terms of cosine. There are no sines at all on the right-hand side. So let's replace sine squared A with something that is equivalent to that. So let's rewrite our identity, our Pythagorean identity, just to be sine squared A by itself on one side. So using our Pythagorean identity, we see that sine squared A is exactly the same thing and can be replaced with an equivalent form, 1 minus cosine squared A. So we're going to bring down the first cosine squared A, minus, and then behind that minus sign, we're going to replace sine squared A with 1 minus cosine squared A. So in order to simplify, we will need to distribute the negative. So we get cosine squared A minus 1 plus cosine squared A. And then we have like terms. That gives 2 times cosine squared A minus 1. And that was our goal. So we have verified all 3 double angle identities for cosine.